give a demonstration of the show and tell. So let's welcome Dion.
So my name is Dion. Then today I'll be giving an example of how we can apply computational thinking to our real life. So our topic for today is Dijkstra's algorithm. This is how you pronounce Dijkstra. Yeah. So it's quite a well-known algorithm. So some of you all might have heard it. But before we go into that, so we start with something more relatable. So today is the first day of school, and I'm sure most of you are like happy to be back, like full of energy. Yeah. So let's put ourselves in the shoes of a freshman who first day of school. So he has this problem. So how do I go from SOE to SOL? So actually, this freshman, right, he had a class in SOE in the morning. Then he had a very short break for him to go to SOL. So he wants to get there in the shortest possible time. But then because he's unfamiliar with SMU, he doesn't know what's the fastest way. So he decided to ask some senior. So this senior, right, happened to have this map of SMU. So he gave this map to the freshman, good for the freshman. But then, upon first glance, right, the freshman can't tell he still can't figure out what's the fastest way from SOE to SOL. So he's stuck. So what I have described is a very simplified version of the shortest path problem, like getting from point A to point B in the shortest possible time or distance. So let's help him solve this problem together. So firstly, this is the map. If we were to look at this map closely, you can actually count out all the possible paths based on the direction. There's only actually a total of 7 ways. So in this case, right, if we were just to count manually and then like for every path we just get the total distance, then we'll get our answer quite easily. But what if there is a lot more points in between, or like there's a lot more different stations? So is there a better way for us to solve this problem? So actually there is. This algorithm is actually called Dijkstra's algorithm. So you will always give the optimal solution, in the sense the shortest path or maybe time to go from point A to another point. And the only assumption we need is that we have positive edge weights. So what does positive edge weights mean? So between any two locations, if you can go between them, right, that's called an edge, like connecting these 2 points. So let's say you imagine a road between like two locations. Then if the road's not there, then there's no edge. And it's quite reasonable to assume positive edge weight for most real life applications, because usually there's no negative distance kind of thing. Yeah. So how does this work? So basically this is a network model. You might have seen it if you've taken decision analysis before. So we have a start and an end. So so the letters represent, like, we call it nodes, but basically it's the distance, it's locations, they represent locations. Then the arrows represent the direction you can go. Sometimes it's 2 ways, sometimes it's 1 way. And the number represents the weight, which is how long it takes to go by that path. Yeah. So let's say we were to start from A. So how this algorithm works is we start from A. We have 2 neighbors, which is B and C. So what we do is we write down which node they came from. So in the case of B, right, it came from A, and the distance is 3. So we're just going to write the number A3, A2 like this. So once all the neighbors of the start node is done, right, we will now look at which of the remaining nodes has the shortest total distance. In this case it's C. So now we'll start from C. So C is the current shortest path. And then we will go to its neighbors, which is E, F, and D. Yeah. And then same thing, we will then so we will just take note of which node it came from and the total distance so far. So from this point on, right, C is done, because now we know that the shortest path from A to C is 2. Yeah. And then we'll not consider it anymore, so we'll cancel it off. So from these remaining nodes 3, 5, 6, and 7, which one has the shortest path? It's actually B. So from B, right, we'll visit all its neighbors. So it's E, F, and C, but C is solved already, so we don't care. So So for E and F, so let's say right now the distance to B is 3, right? So if we were to go to E, right, we'll sum 3 and 4. This will give us 7. And then it's the same as the current best solution there, so we don't replace it. For this, right, 3 plus 4 is 7, so we do not replace the current solution. Yeah. And then we repeat this, we take out B, we go from D. D to F is 5 plus 2, 7, also don't take out. Then we go to F. F to G, right? So 6 plus 3 is 9. And then for E, right? E to G is actually 8. So if this solution is better, what we'll do is we'll replace the current solution. Yeah. So once you finish the whole algorithm and visit all the nodes, right? This is how we get our shortest path. Yeah. So I chose this like simplified algorithm because otherwise it's quite heavy. But the real implementation, right? What we require is for every point, you need this set of, we call it unvisited nodes, and then we have a priority queue. So this is a concept that you all will learn during your data structures. But priority queue is basically, right, let's say it's like they will order, it's always sorted in terms of, like, let's say in this case, the shortest time, right, will always be at the front of the queue. So even if I put something in, right, then it will arrange itself. Yeah. So this is necessary to like solve our problem. So you see the algorithm pseudocode is you visit the node which has the shortest path, you take this node out from the visited nodes, you visit all the neighbors and calculate the total distance. You just keep repeating these steps until you finish visiting all the nodes. Your final path is the shortest path. Okay, so what are some of the real world applications of this? So the biggest one is definitely Google Maps. So let's say we were to solve a navigation problem. We don't use the shortest path algorithm. So let's say we have 1,000 connections between like locations, like say 1,000 roads or something. So if we were to do brute force, there will be 2 to the power of 1,000 ways. Why so many? Because for every road, you can decide whether is it on the shortest path or is it not on the shortest path. And every road is like a yes and no decision. If we have 1,000 road, 2 to the power 1,000 ways. So let's say we were to use our smartphone, 1 gigahertz processor, to the power 1,000 times 0. So there's 10 to the power of -9 here. It will take like ages, it will take forever basically. So we cannot do it brute force definitely. So what we do, let's say with Dijkstra's algorithm, we have 1,000 locations. Even in the worst case scenario, there'll be at most 1,000 squared calculations times the number of times it takes to process. So 0.001 seconds, which is quite fast for, it's a very fast calculation. So even though it might not give the best, because like it can be the shortest path, but maybe there's other things to consider like transport costs, all this stuff. So it might not really be the best out there, but it's a reasonably good solution and it's quite quick. Yeah. So let's say we are to show, this is a map of Seoul's MRT stations. And let's say we were just to choose any 2 random points, let's say one here and one there. How to find out what's the fastest, what's the best way to get there. So that's another application of Dijkstra's algorithm. So you really save a lot of time, like because there's so many different like lines and all that. And other real world applications would be like telephone lines to consume the least bandwidth. Network routing, actually this is a very big application also, like because the internet, like usually you do not directly communicate with your source. Let's say like that website is in another place, then you have to route to the school first, then to maybe Singapore, then to USA, and etc. Yeah. And last but not least, we have shipping delivery systems, like what's the fastest way to deliver. Yeah. So that's all. It's a